So the aim of our project is to develop and demonstrate a platform on DAFNI for understanding and simulating urban drainage for any city in the UK, and also provide the functionality that consultants and researchers need in order to test a range of strategies to mitigate storm overflows and surface water flooding. So the modeling system is based on CityCAD, which is a hydrodynamic model, which has been built at Newcastle University over the last 15 years or so. It can be used to model pluvial and fluvial flooding, and it can also be used to model explicitly blue-green infrastructure like green roofs, permeable pavements, and all this. It uses standard inputs, for example, LiDAR topographic data, and also it uses the master map dataset to extract buildings, roads, and green areas. The main components of the model are the numerical grid generator, the surface flow model, which is based on the shallow water equations, and these equations are solved using finite volume shock capturing schemes. It has also an infiltration model, which is based on the cleanup method and the Richards equations. It has also a roof storage model and a pipe network model, which is based on the mixed flow equations and is fully coupled with the surface flow model. In terms of output, what we get is maps and time series of water depths and velocities and flow conditions in pipes. So the main difference of our model compared to other models is that is the pipe model. So basically it's based on the free surface and pressurized flow equations, so you can model accurately free surface, pressurized, and mixed flows in pipes, and it is fully coupled with the surface. But the problem with this approach is that it's a bit slower. So that's why we really need platforms like DAFNI to run these models, because they do take quite a bit of time to run. And in some cases, the pipe network, the drainage pipe network, is important. So the plot on the left shows the results from a surface flow model only, and then the one on the right shows the results from a fully coupled model. So we can see the differences in water depths. But there are lots of drain inlets in that area, and a very big underground pipe, like the diameter I think is 2 meters. And here, if it works, we could see that basically the water depths and velocity vectors, plus the amount of water that is captured by the inlets. So as I said before, we can also use the model to model blue-green infrastructure. So you can add basically here, in this case, we have green roofs and permeable pavements, and the plot on the right shows the reduction in water depths. So CityCAD on DAFNI. So the model was already deployed on DAFNI like as part of the Open Clean project, like probably around 3 years ago. Don't remember exactly, but the first workflow allowed users to assess flood risk for any city in the UK for a range of storm events, but it had limited functionality, so it couldn't really be used to model blue-green infrastructure. So, as I mentioned earlier, our project aims to develop a platform on DAFNI for understanding and simulating urban drainage, and then also provide the functionality to design and test a range of strategies to mitigate flooding. So then, in order to achieve this, we need to do these 4 things. So we need to extend the functionality to allow users to assess the effectiveness of blue-green infrastructure. Then we need to develop an optimization tool in order to determine the optimal location of blue-green infrastructure. Then we need to develop another tool to visualize and use the pipe network in order to be able to build fully coupled models, surface-subsurface. And then at the very end, we need to develop a methodology to explore a wide range of rainfall events and design constraints. So far, managed to do the first two. So now users can use the workflow to model blue-green infrastructure. As you can see here, we can add green areas, permeable pavements, and you can see the reduction in water depths on the right. And then we also developed an optimization tool, which is now deployed on DAFNI only recently. So this is a very simple example, right? So let's say that this is our urban area, and then we divide this area into 12 zones. And then we want to work out where to put permeable pavements, okay? So every solution is presented by a string, and then when we have a 1, it means that we implement an intervention in the corresponding zone. 0, when we have a 0, that there is no intervention within the zone. So when you have 12 zones, the possible combinations that you get is 2 to the power of 12, so 4096. So basically, you need to run the hydrodynamic model 4096 times, and that takes quite a bit of time. So here on this graph on the right, you see all these possible solutions. And the ones that are highlighted in red are referred to as the Pareto optimal set. So basically, these are the optimal solutions for any given x and y. But 12 is not enough, these zones, yeah? So probably we need about 50. So then it becomes impossible. So once this number of zones grows, then the other one, the possible combinations grow exponentially. So then but then we can employ an optimization technique in order to approximate this Pareto front. Yeah. And then once we have that, then practitioners can use this in order to make an informed decision. The first two are very standard, the SPE2 and the NSGA2, pretty standard algorithms. They do work quite well, but we found that the epsilon multi-objective evolutionary algorithm is a lot faster and it's a lot more flexible. So for example, you can set the maximum number of solutions that you want. It has an adaptive size, population size, and actually the self-determination criteria actually works quite well. So all this now is on DAFNI, and we have tested it quite a bit. So you have a point is represented in the model and during a simulation. So then it changes the dimensions here, then you could see the dimensions, and then you do have to provide some constraints, but then at the end you get the final the dimensions of that point. Yeah? That's for the epsilon one. So the epsilon always starts from 5 and then increases the population, and then we set the maximum number of solutions to 100, and then you could see moving that way. So here is on the x-axis you have the installation cost, and on the y-axis you have the number of buildings at high risk of flooding. So basically you want to go down that way. Yeah? And then you can see that then it creates a lot of solutions, and then it moves that way. So, and that takes quite a bit of time because you have lots of points. 100 solutions means that you have lots of points on the Pareto curve, and it takes about 3 weeks to run this. But then if you set it to 10, then it takes probably 1 day, and then it's quite close. It's not perfect, but you lose some information obviously, but if you want to get some results quickly, then this might be an option. So this is a comparison between these two with 110. So this is here. This is solution 1. So basically here the areas highlighted in green are the areas where permeable pavements are implemented, and then here you can see the ponds. And then the second one, you see there are no permeable pavements, there are only ponds. And then the third one, you have a lot more permeable pavements, and then you have a lot more, and then some buildings from red, which means that they are high risk of flooding, they move from red and go to gray, which means that this number of buildings at high risk goes down. So this is basically what the model does. So far, we haven't really used the results from the project or the work we've done. We've used only some of the results when we organized Northumbria Water Innovation Festival in July. And we are also involved in the Newcastle Blue-Green City project, which has just started. And then the Newcastle City Council are very keen to use the results from the optimization. And next steps, we need to do this too. So we started working on the pipes and the scenarios. So, thank you.